Hello friends, I welcome you all to this video. We are with the last video from the chapter 2 of Advanced Digital Signal Processing, the chapter devoted to learn multi-rate digital signal processing. So in this chapter we started to know what exactly the key and very popular operations for multi-rate DSP. Those are interpolation and decimation. We have also understood the concepts along with the MATLAB demonstration to illustrate these key operations. We further have seen the multi-stage interpolation decomposition, the decimation polyphase decomposition basically, and then the quadrature mirror filter bank here. The various applications of DSP have already been covered here. Now in the previous video we have seen the MATLAB demonstration with respect to the quadrature mirror filter. Now let us work with the QMF filter bank in this video. So let us begin with the topic. So here we start with our topic, the topic titled MATLAB Program Performance of QMF Bank here. So to accomplish this particular task here, a simple objective we shall be taking to work into the MATLAB environment. It will be write a MATLAB program to illustrate the performance of QMF bank. So the program statement to be implemented into the MATLAB environment is very straightforward. It is not provided with any of the input data or expected output data. So whatever the filter coefficient we will like to have as input, those we can be taking in real time from the command prompt. So let us first of all switch to the MATLAB environment where we can have the programming for this task. So in this MATLAB environment we require a new script to program for. So here we have taken, so we want the initial windows from the results of the earlier programs to be getting closed. The variables into the workspace will also be getting cleared and a clear command prompt here. Next to that we can program, and after the execution there it will be a press execution, so with only the results associated to this particular program here. So I first of all mention a comment line to show what is the purpose of this particular program. So this is a MATLAB program, so I just mentioned this is a program, and this is a program with respect to the QMF filter bank. QMF standing for quadrature mirror filter bank. The concept we have already learned. The corresponding block diagram are definitely explanatory to hold the understanding of this particular filter banks here. Now this is a program for the responses of the filter bank. So responses are of course into the frequency domain, hence I mentioned program for frequency responses of. As the block diagram we have seen with respect to the QMF filter bank, we can call it to be a tree structure also. So this is tree structured QMF filter. Now here we require first of all the initial coefficients as input, and with the help of those initial coefficients we can have the filters into the use here. So as into the previous video we have accepted the input coefficients from the command prompt, assigned it to the variable capital B1. We shall be again doing the same, and then we shall be having a tree structured QMF filter bank with the 4 filters. So here initially I shall be having the comment to write the initialization of the coefficients here for the low pass filter, hence I mention enter the low pass filter coefficients. So these filter coefficients initially we are going to assign to the variable capital B1. So here the assignment will be by the MATLAB syntax input, and within a pair of parentheses and single quotes we mention the message onto the command prompt, enter the filter coefficients. space equal to sign space, and at the end with the help of semicolon we can close this syntax. Now whatever the number of elements we are going to take as input and assigning it to the b1, in actual what we are going to do here, b1 we are assigning with the help of array those has the initial elements b1 as it is, and next to that we append the flipped version of the b1 sequence here. So for flipping left to right, here we are going to make the use of command. So flip_lr is the command here, and the input variable can be capital B1 here. So whatever the total number of filter coefficients you accept from the command prompt, in actual double the number of filter coefficients we are assigning to capital B1 as variable. So now this is the simple low pass filter with the filter coefficients. Now we require another complementary high pass filter. So for that purpose we separate out the script with the comment line generation of complementary high pass filter. So here the length of the high pass filter we are going to use the same as we have for the first filter. So the length can be declared with the help of variable capital L, and to equate it with respect to that of the first filter we assign it the same, hence the syntax length, and the input is capital B1 corresponding to the first filter here. So now formulation of the filter coefficients we are going to make with the help of the first filter coefficients. So for the entire length we can be computing it with the help of for loop. So for loop we require the index variable as before we shall be selecting it to be small k here, and that we can initiate at 1 and it will last up to capital L, that is the length of the filter we have just now formulated here. So it is the same length as that of the first filter. Now under this for loop the computation of the filter coefficients we shall be making and assigning it to the new variable. That new variable we declare to be capital B2 here. So for capital B2, inside the parenthesis we specify the index variable small k. We make the computation by having -1 to the power k here, and outside it is having the multiplication to capital B1 of k here. So with this formulation whatever the filter coefficients associated with the first filter are there, so if it is low pass filter it will give us the high pass filter here. So ending this formulation with the semicolon, and now the task has completed, hence the for loop should also be ended here. So after ending the for loop, now we have to determine the filter coefficient for 4 filters using these two, so that we can have the quadrature mirror filter bank here. So for that purpose here I mention determination of coefficients of coefficients of 4 filters. So let us say initially from the first filter B1 we are getting the variables at intermediate level B10, and initially we expect every variable there with the 0 value, hence we use the MATLAB syntax zeros and define its particular length by 1, 2 in multiplication to the length of B1 here. Next to that, this B10 we are assigning for the specific range right from 1 with the interval of 2 up to the length of the same filter coefficient variable b10 by, here we are going to make the assignment by b1 here. So this way, for the first filter out of the 4, we have b10 formulated here. Next to that, b11, the intermediate filter coefficients, again initially we expect them to be every element value 0, and the range here we can specify 1 comma 2 in multiplication to the length of, here the variable we assign b2. The second filter coefficients that we have formulated from the b1 accepted as input from the command prompt are utilized here. So here upon b11 is also make the assignment to the specific range initiated at 1 but with the intervals of 2 up to the length of the filter. So this is the length, and the input variable is the same here, that it is b2, and this is equal to capital B2 here. Now exactly the 4 filter coefficients we can name as C0, C1, C2 and C3 that we have to determine, that we have to formulate. So for that purpose we take C0 initially and we obtain it by the convolution function. So as already we have practiced the convolution operation into the MATLAB syntax here, so it has CONV as the MATLAB syntax. The input can be capital B1 and another signal, the discrete sequence I can say here with which we have to carry out this convolution procedure can be B10 here. So here I end this syntax line by the semicolon here. Now we go for the formulation of second filter coefficient. So let us name it by C1, and again we are going to compute it by the use of convolution. So conv command, and this time we are assigning the input parameters for convolution process B1 and B11. So this time we have different combination of the convolving signals that will produce the resultant filter coefficients. So C0 will be obtained for different, C1 also obtained for different. Now it's time for C2. So for C2 again the convolution we have to carry out, and the input parameters are B2 comma, here we provide as input B10, and in the similar fashion the last filter coefficient C3 can be computed by having the convolution operation, and this time the inputs are B2 comma capital B11 here. So this way the determination of the filter coefficients corresponding to the 4 filters have been done here. Now it's time to have determination of the frequency responses corresponding to these ones. So here I just mention a comment to separate out the body of that MATLAB program. Determination of frequency responses. And hereupon, as the frequency plot, frequency domain information can be obtained with the help of the two variables, one to hold the representation of frequency domain by the variable W and another to hold its amplitude or magnitude, you can see here. So corresponding to the first filter, here we are obtaining the information in terms of capital H0Z comma W here. And this can be obtained as usual. For obtaining the frequency response we have the MATLAB syntax FREQ Z here, and thereupon the inputs we are providing the filter coefficients of the first filter C0 comma 1 comma 256 we are providing as limit. Next to that we want the response here to be plotted here. So for this particular magnitude we require the absolute value of this capital H0Z. So for that purpose we take small h0 and assign it with the value absolute of ABS in bracket capital H0Z here. Next to that, if we require it to be plotted with the help of decibel range here, so for that purpose we have to take logarithm over the value obtained. So for this magnitude into the decibels here, we take the variable capital M0 and we compute it by 20 in multiplication to the logarithm to the base 10 operated over small h0, which is the absolute value of capital H0Z here. So this way the magnitude corresponding to the frequency response of the first filter in the QMF filter bank here can be made available. So in the similar fashion we have to go for second filter, third filter and the fourth filter. So for second filter the frequency response is to be again obtained here. Now this time the variables are named as capital H1Z comma W. This obtaining can be made assigned by FREQZ operated over filter coefficients C1 comma 1 comma 256. Next to that, the absolute value obtained at H1, so ABS of operated over capital H1Z, and then we have to get the value in terms of decibels. So for that purpose we take M1 as the variable and compute it into the decibels here. So this is 20 in multiplication to, here we have log to the base 10 of, so here we make small h1 as the input that has been computed into the above step here. Next to that we go for working at the frequency response of third filter. So for third filter frequency response we have H2Z as the variable to hold the magnitude responses into the frequency domain, hence W is the variable. The MATLAB syntax is FREQZ and the input is now we have C2 comma 1 comma 256. So now the absolute value can be assigned to small h2. To the small h2 the absolute ABS command and the input variable is capital H2Z here. And now the magnitude can be holded by capital M2 computed as in the logarithmic case 20 in multiplication denoted by asterisk sign in the MATLAB syntax to the log to the base 10 log log 10 here, where we have the input as small h2, the result from the above step here. Now for the last filter we have the assignment to capital H3Z comma W by the syntax FREQZ for the frequency response, and the input operands are C3. The coefficients of the fourth filter, those have been computed by the convolution operation for B2 and B11. So now we have 1 comma 256 the input variable values here. Then we obtain H3 to be the absolute of in the transform domain capital H3 Z here. So it is the usual practice that when we have the representation into the transform domain we have the notation with the help of capital letters, and when we are back to the parent domain, so that time we have representation by small casing letters here. Now the magnitude we assign it to the variable capital M3, and here we make it assigned by 20 in multiplication to log to the base 10 of the variable computed in the above step is small h3 here. So this way we have all the magnitude values corresponding to the filter responses of the four filters. Those are a part of quadrature mirror filter. So four filters here. So QMF filter bank, here it is. Now it's a part to have plotting of these filter responses, the gain values here. So I just mentioned plot the values here or plot the graphs here. So for plotting purpose, we shall be having the simple MATLAB syntax plot function, and the input parameters we specify w divided by pi, comma, capital M0 holds corresponding values of the first filter, comma, here we provide 1 dash within a pair of single quotes. Next to that, in the similar fashion, for second filter we have w divided by pi, comma, capital M1, comma, here we have 2 dash, then comma, w divided by pi, comma, here we have M2 values, and then we can have the assignment by double dash and separating it to the last filter values here. So for the last filter, here we have w divided by pi, comma, capital M3, comma, here we separate out by a dash here, and we want it all in the grid form. So by the next line, we can have labeling to the corresponding axis. So to the x-axis we mention x label, and thereupon we specify the representation by the omega symbol, that is why slash omega in the MATLAB case, which is divided by pi symbol, omega by pi here. So slash pi to print the pi symbol here. As like the x-axis, we also have to label the y-axis. So y label is the MATLAB syntax, and thereupon we print the name. These are the values of gains, and those have been computed in terms of decibels, hence dB is the unit of measurement here. So this completes the MATLAB script for this particular task. So now we have to save it. So let us save it by the name program 2_20. So .m will be the file extension. So we have saved this MATLAB script for the corresponding frequency responses for the QMF filter bank here. So now let us execute this program. So as we execute this particular program, there it is, a string displayed onto the command window. So onto the command window, it is asking us to enter the filter coefficients. So the filter coefficients, a group of filter coefficient values we have to provide in terms of array, hence within a square bracket I shall be providing the inputs as, let us say, 2, 5 and then 10. So just now I provide 3 filter coefficients. So these will be assigned to the variable b1. Next, as per the script, there it will be 2, 5, 10 and the flip version of these variables here. So it will be the first filter coefficients b1, then it will be the computation of b2 by the use of for loop, then by having the convolution operation with the different combinations, we can have the 4 filters, those form the QMF filter bank here. So let us hit enter to see what has been plotted as the gain corresponding to these 4 filters, a part of QMF filter bank here. So as we can see into the MATLAB script, while having the formulations of B10, B11 corresponding to the B1 and B2 here we expect B11 with the range 1 with the interval up to 2, at max the length of B11 here, which is assigned to the B2 here. Then we can have the convolutions operations and the corresponding filter coefficients C0, C1, C2, C3 can be computed. So with this correction here we can run this particular program, and now it is asking us to enter the filter coefficient values here. So in the array, as we are providing only the 3 values here, 2, 5, 10 here. So as I hit the enter, you can see this is the MATLAB window that has been generated as output here. Onto the horizontal axis we have omega divided by pi, so it is running from 0 to 1 here, whereas the gain in terms of decibels is plotted right from -60 decibels to +80 decibels with the intervals of 20 decibels onto the vertical axis here. Now as I maximize this window in this particular plot, you can find the 4 plots here. So the one plot, that is the continuous line, the line with the color blue here. There it is another plot with the continuous line with the violet color. Next one, we have a dashed line with the yellow color here, and another one dashed line with the red color here. So the four plots are corresponding to the gain values of the four filter coefficients here. The four filters, those are a part of QMF filter band. So the initial three filter coefficient values that have been assigned to the B1, so with 2, 5 and 10 value, we have obtained these plots here. So the gain value at any of the point in this particular grid format, we can note down for any of the filter. Let us say for this violet color, the gain value is 14.75. So at the highest value, as we can mark 47.05 in decibels here. So for the blue color, the least values can be obtained here with minus 5.94 decibels here. So I just close this particular window and I just run this particular program again, and now this time I shall be providing the filter coefficient values, few of the filter coefficient values with the negations. So let us say this is minus 5, then plus 4, next to that minus 2, next we have 9, next we have minus 3 here, next to that 10, next to that we have 4, then minus 1. So these many filter coefficients I provide as input and just hit the enter. So now you can see with the increased number of filter coefficients as input, the complexity has increased into the plot that we have obtained. Still we have the four plots corresponding to the gains of four filters, a part of QMF filter bank here, and we have a lot of variation into the values. There are different peaks and the drops in this particular plot. The corresponding values can be noted into the decibels for the gain here. So this was the simple MATLAB demonstration with respect to the performance of QMF filter bank here. Now by the next video we shall be starting the new chapter in this particular subject titled Advanced Digital Signal Processing, and we shall be studying the discrete time random processes before starting to learn the power spectral estimation with respect to the random processes. Thank you.